Yeah, so, and we are recording now. Yeah, so hello Zoom room, hello real world physical people. Yeah.
I think you can keep it on the Zoom.
Like 4 people now. We have to go away.
Yeah, 4 people. Wow. I guess it also comes from me saying it will be recorded. I guess people used it. Yeah. Anyway, okay. I was thinking about doing exercises related to differential equations. If you want to see any specific exercise, we can still do this. Yeah, just let me know. But I guess there are a lot of question marks around differential equations because they were just introduced in the lecture as far as I know, or at least the Laplace transform is kind of introduced. Not so sure about that, but today we will just see how we can do a calculation with those. So I just picked the next exercise, more or less, in the exam I was also using last time. So yeah, right, there it is. So exercise 4, Laplace. Maybe I should brief recap what this is about. Yes, I see, yes. Yeah, so differential equations are useful, and it's often the useful thing to do is to find some closed solution. Not always. I mean, in really interesting cases, you can't anyway, but in these cases, you look at in the course, you can actually solve differential equations. And Laplace has a nice trick which helps you to find solutions to a particular form of differential equations. So usually you have functions on the reals from real to real, and you have some derivatives. So I guess in the exercises once or twice deriving, and you have some linear combination of those. Nothing else. So some linear relation between the function and its derivatives, and some values like what should f of 0 be, what should f of f prime of 0 be, something like this, because that's something needed to give you a unique solution. Otherwise, you have lots of solutions. Okay, so there's like, I looked around a bit in the exams, and there's like this exercise pattern where it first asks you to find a solution assuming everything is a power series. And then it asks you to find a solution without that assumption by using Laplace. Okay, so let's start with the power series thing, and keep in mind you are welcome to interrupt me, and you can repeat concepts like power series. Yeah.
So it was one way to solve differential equations, to assume that they can be represented as power series.
Yes.
So that means that all functions cannot do that, right?
Yes, you have, I mean, you have functions which are not differentiable. Like in math, such functions exist, and there's no hope to represent them as a power series. And then you have functions which are maybe once or twice differentiable, but not any more times at all points, or even at all. So the process could stop. Then it's also, there's no hope. But then the smooth functions, so those which are infinitely differentiable, for those you could hope that they are always a power series, but that's not true. So sometimes that's not the case. But I mean, for the most functions, you know, it is true. So polynomials, no problem. They are even a finite power series. Exponential functions, sine, cosine, everything is a power series. So yeah, I don't know. I didn't bring an example, but there are power series, and usually there are functions which are not power series, and even reasonable ones. Yeah, but yeah, I didn't bring an example. And there's a cooler version of analysis where you do everything with complex numbers, and that's actually true that everything is a power series. So it's only due to working in too much real world based math. Yeah, anyway, but not every function is a power series. Okay, so I'll write down the system we have to solve. Is f prime equals f plus g. So that's also some special kind of thing where you have two equations which refer to each other. There will also be an f here. And there you have exp. So I just write e minus 4 times g minus 2 times f. And as I said, you need some initial conditions. They are sometimes called, because this is used a lot in physics, which tell you in this case what the values of f and g will be. Yes.
How would we handle if the points are not at 0? So if we have like f of 1, for example, when doing this kind of stuff.
Good question. I would assume
if you have all in the same point, it's doable. But when we do different points, it would not be with our current system.
Yeah, I mean, what I would try to do if I ever end up seeing something like f of 5 equals 1, you can substitute and say, I have some function, maybe let's do it here. I have some function h, which is f of x minus 5.
Yeah.
And then I transform my system to say something about h, and I probably get a, let's state it like this, and I can figure this one out. So I mean, this is f prime of x minus 5 plus f of f times. So something like this, f of x times x, no, 1. Yeah, okay, so it's reasonably simple. I mean, you have almost a linear equation here for f prime with respect to h prime. So that's what I would try, but I mean, if I would guess if exercises deviate from the usual pattern where you know what to do, there will be some hint what to do. Yeah, but good point. This will turn out to be important that we know the value at 0 and not somewhere else. Yeah. Okay. Yeah, and now the first task is solve assuming f and g are power series. Okay, and yeah, how does it help us? We learned how to integrate a power series. And with integration, we can remove the prime. And then we have a relation which refers to f and something integrated, which first sight might not look like much of a help. But yeah, someone in the internet said, perhaps I'm wrong, but I don't think time shifts are included. So there's a rumor that this won't be necessary. Yeah. Okay. I haven't seen it also, but I mean, everything can happen. And self-assuming f and g are power series. So what does it have to do integration? Well, it's a bit tricky. So it kind of shifts the list of coefficients, and this allows you to compute your coefficients of the power series representing f iteratively. So that's something that works. So maybe let's briefly remind ourselves what we can do with power series. So, I mean, if you have a power series, which is given like a list of coefficients, you can certainly derive it. And you have to think of it as, well, something like this. So, and deriving you can do with each sum separately. So at each summand we will kind of get times I, and then we will shift the whole thing. So what happens in the end is we get a new power series if we derive here, which drops the A0 because it's just constant vanishes and deriving stuff. Then we have 1 times A1, 2 times A2, 3 times A3, so forth. Okay, and now for integrating, we have to reverse the process. So if we integrate a power series, we have to give a constant. So this will be the A0 and the power series. Let's call it like this again. And it should be the inverse operation. So we, not 0, C. We put in C here, and it's 1 times A0, A1 half, A2 thirds, dot, dot, dot. Yeah, right. And if I apply this again, I get this one back. Okay, so how can it help? How can we remove the prime? We can do it by doing something like this. If we plug in f of 0, which is a naught, the power series representation, we can kill the prime. So if this is a power series, this will be f again. Right, yeah. Okay, so one way to solve this would to apply this function on both sides. Then we get something which doesn't contain a derivative. So our solution could be apply this on both sides. So integ f naught. And maybe I should be a bit more explicit about what arguments are and what not. So maybe more like a Haskell syntax like this, and f prime here. And I can apply it to this whole thing. Okay, and this evaluates to f. So now we have something we could solve if we knew G. But we can do something similar for G, or actually pretty much the same. So right here. So just do the same with G0 and G prime here. So we have G equals integration of that with constant term G0. Okay, now, so how can we calculate with this stuff? What simplifications are allowed? Just talk to me. It prevents you from getting sleepy.
No, but we have lists, so we can just look at them as lists. And since we know the first column in some of their lists, we can verify what the others should be.
Yeah, I mean, that's something we can
If we do
start
it
at
like
any
that.
moment. Yeah. Yeah, sure. Then let's just do it like this. So, I mean, we're assuming G is some stream of coefficients or some lazy list in Haskell, and F as well. Yeah, so maybe we just write it out here. So it's integ of, and maybe we just plug that in, 1. And over here we have added element-wise these two lists. So that's the list A0 plus B0, A1 plus B1, and so on. And yeah, should we do the same thing here? Or simplify before that? I mean, we could, yeah. Hard to tell what will be easier, I don't know. So yeah, E is also a power series. So what is E? E as a power series is just 1. Are the first two ones? Yeah.
And then 1 third factorial.
Yeah.
And so on.
Okay. Yeah, let's hope we don't need too much of that. Yeah.
Wait. Why are there 2 ones?
Because first 1 and then 1 divided by 1. And then 1 divided by 2 factorial.
But isn't the first one 1 divided by 0 factorial?
Yeah.
Factorial 1.
0 factorial is 1.
Okay.
Yeah. But yeah, I guess it's good to write it out. Yeah. So x0 is 1 over 0 factorial. So let's evaluate 1 x over 1 factorial. Yeah. Yeah. I mean, this is essentially an empty product. And if you have, like, if you extend operations to lists, so operations in a monoid to operating on whole lists, you should take always a neutral element for the empty list. And the neutral element here is 1. So empty list multiplying everything in an empty list should always give 1, and adding everything in an empty list should give 0. Yeah, that might be the tricky point here. Okay. Yeah, also maybe one point. that appears sometimes even in math lectures as something that is kind of not well defined. 0 to the 0
Is 1.
Zero
Yes.
to zero is one.
It's
the
one,
zero
yeah.
is more important than the base zero.
it's 1, but sometimes people not further away from pure math, where you have like good principles for something like this, will tell you it's questionable what you should take as a value for that. So yeah, you can tell them, no, it's 1, if you like. Anyway, okay. Yeah, so we could just plug in everything. We also know G of 0 is 3. And yeah, maybe let's just do this list in one go. 3 and so is it really good to do it like this? I don't know.
This was not how I intended, but yeah, it doesn't look that nice.
I mean, what's the alternative? It would be to split this all up. So we can use that this operation will be linear. So we can integrate each thing separately. It might help. It's not so clear. So any preference? I don't know. I would split it up. But yeah, let's just don't. So what kind of list do we get here? So we have the first one is from E, so it's 1. And then we have -4 times the first coefficient of B. So it's -4 times B naught. And -2 times, I guess that actually works well enough. So, okay, so the second is again this -4 times. Yeah, right. It's abstract enough to not be annoying. And now we can just look into the exercise, how much we are supposed to compute. I mean, that's what we need to solve, blah, blah, blah. Express the relation between everything. What are the first 3 coefficients of F? Explain how you compute them. Okay, first 3 coefficients should mean we only need these 2. Because when we integrate, we inject 1 coefficient in the front. Okay, so let's try to work with this, and this will also match up with this. So now we can kind of evaluate integ, which we have written up here. So it's a list with that starts with this value 3, and yeah, we got the C. So the next one is just the first one from here. -4 times B naught -2 A naught, and the second one we have to divide by 2. So I just do it in each component separately, I guess. Maybe that's good. Who knows? Yeah. Okay. So now that is close to being numbers. So we already know the first coefficient of G. That's not what we are supposed to compute, but what we will need. And here, let's also evaluate that a bit further. So we have something which starts with 1, and then we have just this thing, and then we have this thing halved. Okay, so this is what we are supposed to compute. These 3 coefficients, the first 3 of F. So we already know 1. Maybe let's find a good spot for that.
No, A0 and B0, right?
A0 and B0, why?
Because we have integrated and we know then therefore that the first of G is 3 and A0 is 1.
Yes, we can continue. Yeah.
So we have more or less solved this, right?
Yeah, we have more or less solved this, but with space, I meant I should switch the boards or something like this to have enough space to write it down properly in a way that everyone can still see, but I guess it works. Yeah, okay, but yeah, you're completely right. So maybe let's mark this in some way and say, from this we know A0 is the first one of these, so it's 1. We were asked to explain something, so we could say something like, my notation is actually not so great. So in the exercise text, which I didn't read carefully, this is called FS. So it would be good to use the same notation, but my screen is very small and pixelated, and so I didn't see it. Yeah, anyway, so A0 is 1. So I reference the exact spot where this is written, so I assume that's enough. And so the next one, I give a bit of a reason. So B0 is 3 because, well, it's written here. Like, maybe call this one star star, something like this. Yeah. So A1 is A0 plus B0, and that's 4. Okay, so the next one is A1 plus B1. So B1 is 1 minus 4 times B0 minus 2 times A0. We know both of these. Am I at the right place? Yes, I am. So this is, what is B0 again? 3 and 6, and this is 1. So we have 1 minus 12 is 11 minus 2 is minus 13. And yeah, don't be distracted if you get large numbers for larger coefficients, because that usually happens when you just throw in equations like this. You will get large coefficients. Minus 13. Okay, so A2 is A1, which we know, plus B1, which we just calculated. So A1 is 4 minus 13 divided by 2. Yeah, okay, we are done. I mean, we can still simplify this one, so it's minus 9/2. But yeah, those are the first 3 coefficients. Yeah, good. Okay, any questions before I erase that for the next part of the exercise? Okay, I guess we can actually just remember the Laplace in principle and then solve the next part after the break. It's probably better. So I'll just erase our calculation here. Yeah. Won't be needed. What might be a good idea in general is to tell you what exercise I'm computing exactly. So it's from this exam from August last year, and the folders in the Git repo are named like this, so that's how you can find it. Okay, but how did Laplace work again? So, that was your phone, not my computer. Good. Okay, so Laplace in general takes a function and turns it into a function. So this is not entirely true, I guess. I'm not sure, but we also don't have to care about. So it might produce some function which doesn't exist like everywhere on R or C or
yeah, he said complex to complex.
Complex to complex. Okay, that's, yeah, sure, that's better. Yeah, we actually need it sometimes that it's a complex function. Yeah, sorry, that's, thanks. Yeah, so in general, it's a complex parameter, and sometimes it's really useful. So you sometimes calculate with complex numbers and e to some complex number, and in the end you get some solution of a real differential equation, which is real again. In between, you had some easier time calculating in complex numbers. Yeah, so that can happen, and it's quite amazing. Yeah, but yeah. So what does it help us? So the general idea is that differentials or differentiating is easier here. And easier means algebraic. So what it means concretely is if you apply this L to some derivative, then you get the following relation. So kind of forget about the last part, it's just a constant, that's not so important here, but
question about that though.
Yeah.
From the definition, like proper definition of Laplace, you have the integral from 0 to x, I think it is.
Yeah, something like this, right? So
is the 0 derived just from the fact that we have zeros as the starting point of the integral? I'm assuming, right? The 0 part f0 is just from the part of 0, right?
Yeah.
Could we change that to use that in some way? Or do we have to have it at 0?
No, I mean, in principle, everything should work if you use some other number, but I mean, you have to rederive everything you know about the Laplace transform. That's probably less pleasant than making some transformation to your function if you have a starting value at some other point. But maybe in some cases it helps. Yeah, okay, so yeah, so I mean, this integral can fail to exist. That's what I meant with not entirely true. So it might not exist on the whole of C, but yeah, this usually doesn't matter. I mean, everything you really need is a small enough domain here to make comparisons between functions, because in the end you use this whole process to make an elaborate guess for a solution, and in the end you test it anyway. Yeah. Okay. But I mean, under some circumstances, you know exactly what things are and where this integral exists. Okay, so here I wanted to say this exactly. So we apply something to our Laplace transform function, and then we get that differentiating in the argument of the Laplace transform is the same as Laplace transform of just the function and multiplying it by s. So that's what I mean with algebraic. So that's just like a linear transformation. And that's really the selling point here, why it can help you to solve differential equations, because if you apply it to some equation, it makes these things go away and gives you stuff that looks like polynomials or rational functions. And that's something that might be solvable. Okay, but we need a bit of other stuff about the Laplace transform. So if you have real numbers, so I give you the typing, like alpha and beta are real numbers, and f and g are functions. Then you can use linearity. So it's, I add some parentheses for the convenience. So you can just draw that out or in. So linear stuff doesn't really matter as long as it's constant scalars. Okay. Yeah, that's something useful. And then there's something which is usually in the exercise text, and this kind of always lets you solve everything. So, so that's like the power move in the whole thing, is to know that Laplace transform of, I think we, does he put the minus here, or, shit, I have to increase my font to see that, but no, the GitHub rendering of PDFs doesn't let me do that.
Alpha times.
It's not minus, he puts the minus on the other end, yeah, times t, exactly, and the minus is then here. Okay. Yeah, and that's very useful because if you solve differential equations like these, like linear ones, it will always, the solutions will always be more or less e to something in some way. At least if you think complex, it will kind of always be the case. And yeah, because it's like the raw material for power series, and yeah, forget about it. That's what you have to know, and then you can solve it, as you will later see. So these are the important points about the Laplace transform, and if you have those, you yeah, you're good. So maybe let's do a break now and solve the exercise after the break. So I would say continue in at 16:10. Okay. Mic is still on, by the way. Just
Are you still recording?
yeah.
Right. I'm gonna go to the thing to just check.
So what parts of the Laplace is from the definition, what are derivations from the definition of Laplace transform in that important things? Because Laplace transform of e to the alpha t, is that a definition or is it derivation from the definition?
That's something you derive from this one.
So more or less, this is the definition of Laplace.
This is the definition, right? So that's a good point, definition of this thing.
And so then the linearity is because, yeah, integration is linear or whatever.
You can do it yourself.
Do what?
Yeah, just derive all the roots.
Oh, right.
Yeah, I don't know how hard they are, but I guess linearity is okay. On this board, you're also not in the.
Yeah, do we want it?
Your choice.
Okay, so it was, yeah, the linearity. What was that? The top one is something we derive from the differential, right?
Yes, that might be the most complicated one. But yeah, we can try it. So, I mean, the obvious start is to just write down this integral with f prime and see if we can derive something.
With f prime. Oh yeah,
In some revision.
You might have to use integration by parts.
yeah, he did it on the left side.
Maybe that's for other things.
Yes.
We have more pens.
No, it's fine.
Right?
Yeah, I have pens as well, but he was stunning with it. I'll do it in a minute.
No, well, I have pens too.
I have them in pens.
Yeah.
Good job.
That was G or was it? Yeah, it was G.
Yeah, I was a bit confused about the fact that you mentioned this. F equals to something that has to do with F.
Yes, that's confusing. Yeah. But I mean it works because of the shift. Yeah.
Yeah, so if you think of it as lists, the representation, right?
Yeah. Yeah, I mean it works in Haskell because of the laziness, but I mean you can use something else. I guess in some other language you use streams.
Yeah.
Of course. Yeah. Bästa wordmärket. What? Bästa wordmärket. Det täckte färgen någon annan. Stockholm. Ja, Stockholm. Jag tror jag kommer ifrån. I have an amazing bookmark. It's covered in paint for no reason.
You're in no.
Yeah, kanske.
I actually understood bästa bookmark. Or what did you say in Swedish for your amazing bookmark?
The best bookmark.
Ah.
Yeah.
Did you say it in Swedish?
It's the best bookmark.
Oh yeah.
Yeah, okay, it's not very hard to guess. But let me be proud of my language. That's kind.
No, that's 56. I need to reread this the entire Laplace transformation section because I'm honestly a bit too lost right now.
I'm a little bit confused about that.
I have.
The S. Laplace is something function to function. This is a function and a constant.
Yeah, good point. I mean, you define a function by what it is applied to an argument. So that's one way to see it. But I mean, in Haskell, you have the convention. For types that this all can be abbreviated like this.
Oh, okay, yeah. So
Right.
then S is the C.
Yeah.
Okay.
So I mean, this gives you can't kill these parentheses, but if you have something like this is something you can always drop, and then you have just functions like our f over there, and then c to c. So you can read it as a function in two arguments, which takes a function and something in c. So that's the same as producing a function which maps functions to functions.
Okay. Yeah, so S can be complex. Okay.
S is complex.
Okay, yeah, then T is just scoped inside the integration here. So T is no argument for
Yes.
the function. Yeah, okay. Makes
Yeah.
sense.
It's only an argument if you use the lim function and then you create a V2 or something, and then it's just a lambda.
Yeah, I mean, it's syntactic sugar for something which might look like this, like T.
Yeah. Okay, yeah. Then it's just scoped in it.
Yeah. Do you even need more than this to do the power series part? Like, because we know if GSS is G prime series, FSS is F prime series, and we have against that relation. We can use the definitions of these based on that to get this and that, and then
No slow. Wait, what did you do?
okay. So we integrate. We have one
FSS is the coefficients of the
F prime series. Yeah, and we know when we integrate, we add the 1 and the 3 here, and we have the entire series for ES. That we got from like this definition, because we know what E is. And based on that, we can take FSS will be F plus G. So 3 plus 1, add a 4 here. Then we can just instantly integrate that to get this. We can do the same thing for GSS, integrate that, get that here, and then repeat for next. Integrate.
Yes, you can. I mean, that's the short summary
That is the
of
short.
what we did.
Yeah,
Yeah.
because when I just watched yours, it went a bit too slow for my personal opinion. So it was like more, I would get lost in that.
Mhm. Yeah, I mean, for me, what I do is I reason, I don't calculate.
Yeah.
Like I apply steps like doing integration on both sides and canceling something. And
yeah, it makes sense, but
so I mean, I work with
in
arguments as long as I
in
can.
an exam, like does that matter? No.
I mean, in this case, you would have still somehow to communicate what you did, and that's maybe a bit trickier in this approach. But I agree, it's very short. And
it's very short, yeah. But like communication, now I did it verbally.
Yeah.
And I think I could get the communication if I did it in an exam. I see this on like example how to solve. I think I'm not seeing the way you did it at least.
Probably not. I didn't look at the solutions. I just did my.
What did you do in the second when you had the first ones?
So I got these. To get this, you just take that and then divide by 1 in this case. This will be divided by 2. This will be divided by 3.
And the rule we're using is integration. Okay, so power series is
because this is just this integrated with 1 before is just this. So we know that this will be divided by 1, divided by 2, 3, 4 in the next series.
okay. It's because the Taylor series looks like that, right? It's the derivative of it.
And that's
No. That's something else.
That's something else. It's closer to what this is. This is the Taylor series for E.
Yeah.
In a way, because we checked what the derivative is of different points, technically, but at the same time, it's the same thing over and over again. So if you integrate this by 1, you would get the exact same series again.
Okay.
Which is confusing.
Yes. Confusing. Yeah. I mean, I agree. I mean, if you can concentrate very well and you have all the stuff in your mind, you just write it down like this. I'm old. I just do a way I know will work, and I don't have to think about much, which is hopefully understandable.
No, I think your method is a bit more. If you haven't seen how to do it before, it would be more pedagogic. I don't know. Word. Language 5.
It's just the next thing is its derivative divided by the index starting point.
I have a question about the lab that we just had. I have gotten like complete, but I still have comments about the lab submission. Does that mean we're finished and we don't have to submit same stuff again, but maybe keep this in mind, or is it we have to resubmit?
I mean,
Because it's not clear.
if I click on this is complete, I would mean it's done.
Yeah, I would think the same, but we still have like a large comment here.
I mean, if this comment doesn't say fix the following, I wouldn't write.
No, that's the proof for what
Yeah,
it's possible.
It's sorry. You look at your presentation.
Yeah, I had this edition yesterday, and we said we would have to resubmit with like one change perhaps, and therefore it's kind of should we not? I don't know.
It was looking.
Yeah, it was about a proof.
No, that part was about we had implemented the reciprocal problem. We had not thought about it as a different function, derivative and derivative, when there's reciprocal.
Yeah, I mean, now it's a problem that I don't know anything
No,
about.
but if you represent a triple as function, derivative of that said function, derivative, and you want to do 1 over that, you have to do some math.
Yes.
And we have not done that wrong, we know. But we don't know if we have to resubmit or no. And no one's in the next room where they should be, so.
David is not around.
No. So.
Okay. I'm a bit surprised. Oh no, I didn't. No, David made breakout rooms. Yeah. So he's around in
Zoom.
In the Zoom. So you could ask him in the maybe he had technical problems and is not in the other room. But yeah. Okay, I guess we can also continue. Yeah. But I mean, if in doubt, write a comment yourself. I think someone should see it. Yeah. The expression for the Laplace of the second derivative with initial conditions is very useful too. Saw it in other exams. Yes, good point. You can actually derive your second derivative thing from this one. So if you have f prime prime of s is then s times f prime s minus f prime of 0, and then you can go on and resubstitute this again. So you have like s times Laplace f s minus f 0 minus f prime 0, and if you do math here, then you will have the standard thing for second derivative. Okay, so let's solve something. We had questions during the break. Yeah. So the question was, I'm confused here, or something like this. And the answer is, you can think of this type as being this type. And then it's kind of, so you're always allowed to kind of drop the parentheses in the end. And then you know how to read it by experience, that these things are arguments. So this type, a map between maps and maps, is the same as functions which map a map and something in the domain of the second maps type to something here. So that makes it easier to work with, and that's what happens here. You have a function and some s from the complex numbers, and then we can just use those two to do something new, which is again a complex number if everything turns out to be non-divergent. Yep. Okay, so yeah, let's solve the exercise, not assuming everything is a power series, but using Laplace. Yeah, so that should vanish as well. Okay, so this is part B. Yeah, and one first step we can do, I guess, is just apply Laplace to everything and simplify, because that will make the derivative symbols vanish. And that's what we want to do as in part A. Yeah. So just applying Laplace transform. And we can use linearity here. And what's a good idea is maybe to just find some abbreviation for Laplace of f and Laplace of g. Maybe let's just say capital F is LF and capital G is LG. So then with these two, we have, maybe let's do this step first, so we can use our formula here for the derivative, this one. So this is S times, at least if you apply it to S. So maybe I should be more correct here. So I'll introduce an argument now, and then I know S times LF S minus F0 will be the thing we had here, and this will be the same as LFS plus LGS. And now I can abbreviate, because now I only have LF and LG. So I have something like S times F of S minus, I can plug that value in, so that's just one. Stitch. Okay, so that's -1, and we use this side here, so that's Fs plus G of S. Okay, so that's some nice simple equation, and there are only two functions, no derivatives. Okay, and let's do the same thing here to the other equation. So maybe we make some names here. So this was 1. And now we apply Laplace to 2. And then we get same thing with the derivative. So S times G S minus G of 0 is equal to Laplace of G prime of S is equal to Laplace applied to this whole thing, which is Laplace of E of S minus 4 times by linearity. So I'm just using that now on the fly. And I'll use all my abbreviations and I'll let that LES vanish. So remember the other important rule, which is exactly about Laplace of E to the something. So alpha times T. Alpha is 1 here, so we get 1 over S. So this here is 1 over S minus 1. So alpha is 1. And yeah, so otherwise we just use our abbreviations and write it again. So S times G of S minus this value. And here we have 1 over S minus 1 minus 4 times G of S minus 2 times F of S. Okay, so far?
Your E was just a shorthand for E to the T, right?
Yes. That's admittedly a bit vague. So this is like this. Okay. If you're getting sleepy, you can compute yourself. Yeah. Okay. Yeah. So we also have a nice equation here. Maybe we should rearrange stuff a bit. So might be good to have all F or all G on one side, also here. I guess it's a good next step. So I could move this F of S over here. Then I have F of S times S minus 1. Maybe I want to move this minus 1. I'm not sure. Looks nicer. It's like this, I would say. Good. And also simplify this. So just sort it out. Yeah, maybe in this case we also want to move the G of S to one side. So we have plus 4G of S. That means we have G of S times S plus 4. And maybe move this minus 3, let's say. So S minus 4 minus S plus 3. Okay, and I mean, now what we have to solve is like solving linear systems in 2 variables, 2 equations. So we have to find an efficient way of plugging one into the other or adding one to the other or something like this. Any smart ideas what we can do, which is not too much work?
Plugging in the definition of G of S from the first one is probably easier.
So plugging in what G of S is into this one, yeah, we could do this, I agree.
solving for f of s.
Yeah. Okay. So let's do this. So we're using 1 here. Okay, derive for 1. And yeah, maybe make sure everyone is on the same page. We're using this. So we just plug in something for GFS. So we end up with an equation only in f of s, which is a bit of an ugly equation, but should all work out well. So I mean, now we have an equation in only one thing, and now the next goal is what? To have something like f of s equals some expression which doesn't involve f. So we have to solve for f of s. And for that, I need some space. Maybe we keep our rules a bit, who knows? So, how can we sort it out? I mean, yeah, we have to move the f of s all in one place, draw them out something, and then divide by that. So I guess that's what happens. So we should do plus this thing. To move it over here, we should multiply that one out and move this factor over there. And then we have something usable. So yeah, I'll try to be explicit. So s minus 1, we multiply this stuff on the left here because we have to. And we move this stuff. So plus 2 times f s. And then we have something left like s minus 1 plus 3. Okay, so we have to move this one over here, and then we can draw out f of s. So let's have some big parentheses here. And s minus 1, s plus 4 plus 2. And this one we can move to the other side. So we have this. At this point, I'm afraid I made a mistake somewhere. So it's good to check in the end if it's actually a solution. And a good thing is the exercise actually asks us to do that. Good. Let's not be afraid. Yeah. Okay. So next step, we divide by this thing. And before that, we should probably clean up this stuff. Right. So can kind of calculate that and move it here. So yeah, maybe let's do this calculation on the side. What is it? So it's not that pleasant actually. It's yeah, plus s plus 7. So we can multiply that with s minus 1. We actually get a square up here. S minus 1 over s minus 1. Really?
S squared minus 6x minus 6. Yeah.
Yes, thank you. I believe you blindly.
I think.
Minus 7 plus 1 is minus 6, so minus 6 is okay. And this is 7s.
Yeah, it is that.
Wait, it's 7s minus s, so it's
6s.
plus.
Plus 6. Yeah.
Let's just say I misheard.
If it's 1 plus s plus 7 times s minus 7 or s minus 1, the last part on the numerator or whatever it's called. Is that a 7 or a 1?
That's a 7, that's a 1.
Yeah.
Why is it a 1? Can you not shorten it with? No, you cannot. Okay,
I multiplied here.
Yeah, that's correct.
I extended with s minus 1 to get everything in one place.
But that is correct now, yes.
Yes, good, okay. It just looks like that. I guess we have to live with this. And now divide by this thing. Okay, so we have s squared plus 6s minus 6 s minus 1, and we divide it by this whole thing here. S minus 1, s plus 4, plus 2. But I mean, good thing we have something complicated like this, because now we can actually talk about what to do in this case. Yeah. So what can I do here to make this one simpler? So it's simpler if it's a product. That would be great for us.
I can't recall what it's called. But you do A, B, C for each of the parts.
I could start with this, but I actually suspect it would be easier if this is a product. So I can just turn it into one by multiplying out and factoring again. So I could say s squared minus s plus 4s, so minus
Plus 3s.
Plus 3s, thanks. Minus 4 plus 2 is minus 2. So I can factor this one. How can I factor it with the PQ formula? So I can say S12 is minus 3/2 plus minus 3/2 squared minus 2, so plus 2. So it will be a real solution.
Square root of 113 over 2.
What?
Square root
I don't like it. Okay.
Square root of 113 divided by 2.
Square root of 113 divided by 2. What?
I just entered it into Wolfram Alpha.
I'm not happy about it, sorry. Wait, I have 9/4 and I add 2. So I add 8/4. So I have 17/4. 17/4.
So it should be square root of 17.
So it's like this.
Wolfram Alpha does not agree with you unless I mistyped it. Does that not say plus 2 at the end? Yeah, that's a plus 2.
It's 4.25, I think, not 17. Or am I wrong? It's 9 divided by 2, right? Divided by 4.
Yes, 9.
Plus 2.
What am I doing? 9 divided by 4 plus 8/4 is 17/4.
Oh, yeah, okay, you did it that way out.
And then I get a.
I didn't mistype it.
Wait, is it
You did. You can just not read my ones.
Yeah.
That's
So-
a 1.
Yeah, that's
Oh, that's very fair.
Okay. Does it help you if I draw my ones American like this?
Help
I don't know.
me.
So that's actually a pretty annoying cultural difference. So when you go to America, to the US as a German, people will always misread your handwritten ones as sevens all the time. So maybe it's the same here. I don't know. But yeah. So let's be explicit about this.
Sometimes, and sometimes
Some of them are clear ones.
I think that since you do the little cross.
Yes, I do it for a 7, but as long as you don't
it is kind of, but you have seen the 7 before.
No, you have to see the 7 at the same time. I know there's a 7 with a cross in that column. As long as I'm not looking at that, all the other ones with hats look like 7s.
Okay, yeah, whatever. We got the solution. We got there in the end.
Yeah, we got there. Let's leave it at that. So it's -3 plus minus square root 17 over 2. Okay, what does it mean for our factorization? That's s minus that stuff. So it's s plus 3 plus square root 17 half times s plus 3 minus.
Yeah,
no, no,
yeah, it cancel out.
Right, so, okay. Okay, this is really not very nice. Okay, maybe we factor this one as well and see if we can mod out something. Maybe. So maybe the other factor is, no, it's not. No, probably not. Okay. But I try anyway to factor the other one. So for this one, we have S12 is minus 6 half. So 3 square root 3 squared plus 6. So that's 9, 15. So yeah, it's -3 plus minus square root 15. Okay, no, we just can't make it any simpler. So we have to do the ABC thing and split it up. Ah, okay.
What do you really need when you have the capital F? How do you get the F? Is it derivative of it?
It's the Laplace function applied to f.
Yeah, so then you can just use the derivative of what is it? Division. Or why do we try to simplify?
I mean, okay, why do we do this? Good question. I mean, the goal is usually to come to a form where you have only summands, which are all of the form something like a number divided by s minus alpha. And we can usually do this if we have a rational function like this. So we can split it up in things like this. So maybe I should call this lambda1, lambda2, s minus alpha 2 plus dot. Yeah. Because then we will know what the pre-image under Laplace is of this summands. It will be e to the minus alpha t. And then we're done. Then we have a solution. Okay, so
You could also derive it, right? And the form it is right now to get f, or no? No, this is not the integration of it. This is the Laplace of it. Okay, yeah.
yeah.
Sorry.
So no worries, yeah. We know what the Laplace transform of the function is we are looking for. So we found that it is a rational function. But now we have to find a pre-image. So now we have to guess a function such that the Laplace transform is this, because we know it is injective in the big L. Okay, makes sense. Yeah, good. Okay, yeah, let's find some space where we can continue our computation. Maybe this part, or maybe just there's no non-relevant stuff we can erase. Maybe, yeah, maybe this I can. We have seen the rules now a couple of times. Okay. Yeah, so what we want is something like this. So we would like to have numbers, maybe polynomials, maybe even just numbers that make the whole thing look like this. So we can start by saying this has to be that thing. Okay. I try to use international one. It's hard. Okay. Yeah. How can I get this? Well, I just take this thing and multiply that thing with it. So and I get these two factors here. I'll just use their product, I guess, because it's simpler. B times this minus 1 times this factor. And C times the first two. Okay. So this thing, that's this multiplied by this, should equal this. And if we assume A, B, C are not rational, but just polynomials or even numbers, this already gives us 3 equations for these 3 unknowns. Yes?
Aren't all polynomials rational?
Now what I mean is we assume it not to be a general rational functions, but yeah, particular ones, namely polynomials. then we know by degree reasoning that we can get some equations here. But I mean, you could also pretend ABC to be numbers. What we are doing here is a guessing game anyway. So if you check in the end, so we can multiply these things out and look what's the coefficients for S squared in each case, what are the coefficients for S, and what are coefficients for the constant. And we get 3 equations with ABC. Okay, so let's look at the S squared case. I'm losing my pen. 7 uses bars. It's called partial fraction extension, I think. Yeah, I'm sorry, it's probably called partial fraction expansion. I'm not sure, I only know the German name, but that doesn't help you.
ABC. What is it?
The
German
ABC
name? You can look up Wikipedia.
Sorry, what?
What's the German name for it?
Yeah, please forget it.
No, seriously, what is it?
The German,
Yeah.
Partialbruchzerlegung.
Yeah, I was naive.
Yeah, I mean, now the question is, can I type it on a Swedish keyboard? Okay.
Men det är partiell bråksuppdelning på svenska.
Yeah.
Yeah.
So,
I never know the math names.
yeah, don't hurt yourself. Okay. Okay, so yeah, let's do the square trick. So it's, coefficient for squares is 1 in any case, so we get this equation. Let's look at the linear. Should I go into more detail? Maybe?
We're running a bit short on time.
Yeah, you have -1 minute left.
No?
No,
You have
14.
15.
Then we have a
No.
Oh yeah, that's in the mornings.
Yeah.
I actually don't really know the schedule, but yeah, so we have 3s times a here, so we get 3a. Here, as the middle term, we get something more complicated, so -1 plus this thing. So we have a 1 here instead of 3. So it's plus 1 minus square root 17/2b. And here we have minus s.
But except minus, is that right? Oh wait.
It's the same, just with, yeah, right. So we have 1 plus square root 17/2c, and here it's a 6. So this should be 6. And now for the constant part, we have minus 2a plus minus actually minus, because it's a product of these two, so it's 3 minus square root 17/2 times b, and here we have minus this thing, so minus 3 plus. And what should it be? Minus 6. Okay. Yeah, now we have to Gauss solve this stuff to get our solution. Where's my, yes. Thing. Yeah. So, I mean, I can just add this equation to this one 2 times and minus 3 times to this one. And then I have a system in 2 equations. So let's start with this one because it's easier. So we get a +2 here and +2 here and +2 over here. So we have how can I calculate +2 efficiently here? It's +4 here, so it's I'll just write it down first. So 2 plus 2 times b, and I have like plus 2 plus 2 times c equals -4. So that's adding, maybe I should hand out some names. So this is 2 times 1 plus 2. It's this equation, and now I do 3 plus -3 times 1. And this will be something similar. So I use the first factor, and then I have -3 here and here and here. So this is C equals 3. Okay, so we can solve these two with these B and C with these two equations. How much time do we have left? Yeah, might work. 9 minutes. Thank you. So yeah, I guess we have to simplify a bit to see how to add things. So this is 4/2. And we can add it here. So we get, I'll just write it in now. So 4/2, so we had a 4 here, so we get a 7. And doing the same thing here gives us also a 7. And we do the same thing here. And we get -6, so we have -5 here. And we get 6 again, so we have okay. So yeah, I guess we have to multiply with the inverse of something like this. Or does anyone see an easy way to solve this? No.
No.
Okay.
Yes, no.
No easy way. I'm still a bit suspicious. There's a mistake somewhere. I calculated this a couple of days ago, but I did something very different. It was
Yeah,
easier.
the solution here on GitHub is also they use a trick midway that didn't use, we didn't get square root in there somehow. I don't see how they did that step. It just says simplify and factor, and then
yeah, okay. That's a bit annoying. So maybe this is because of a mistake, but yeah, it could also just be like that and we are unlucky. So okay, I really don't see a way to get around this. So yeah, I just multiply with the inverse of this here and then times this, because that's what you have to do in this situation. Did the solution solve for f or for g?
for F.
Is it what we did?
They were at this stage.
I forgot by this time.
Simplify and factor.
Ah, we solved for f. Okay.
Oh, simplify.
I mean, I'll try and spend a small amount of time in looking if I see where.
Do you see this this step right here? I don't know how to simplify it. It just says simplify. I don't see how they did.
They did something similar to what we did earlier.
They got at the end like this, which were, yeah, this is easier to do.
And they also have simpler.
Yeah.
Simpler.
Yeah.
Why is it simpler? Okay.
The only difference we have is this step right here. So these are the same things over here when they did the simplified factors.
Okay, this is something we also had.
Yeah, it's the one that is on the second row.
This.
Yeah, exactly.
Okay, why did something bad happen?
We did divide something, but they have apparently done something else.
I'll check this one.
Yeah, this.
Okay. So they calculate these two together. S plus 7, then you get s minus 1. So the 3 cancels.
Oh yeah.
And the right one.
This is shift, and here
multiplying out, adding the two, and then factoring again. I guess, I mean, similar to what we did here in this step, but they did get something better. So I guess this here should be the same as the s minus 4 times.
But we have
S
s plus 4 there. So we have
Yeah,
that's-
maybe there's just a sign mistake.
And that has been
Messing up.
messing up a lot.
Okay, so hello internet, we compared with the official solution and found out I made a mistake here.
And
So-
where does it come from? That's another question.
Yeah, so let's debug what I did, and where is it?
I think you have.
I erased it. Oh, no,
There's no
I
record
erased
except the
the
recording.
That's a recording.
Except the recording.
Yeah,
Yeah, something went wrong somewhere along.
yeah, you can rewind it at home, and let's just see how this makes everything better. I mean, we have a -2 then here. Yeah, okay. I mean, what is learned from that is if you end up with something like this, first thing you should do is look, did I get the signs right everywhere? And yeah, sure. Okay, so what is better than here? So we have +4 then, so this turns into a +6.
There is another sign mistake.
And
Is there another sign
The
mistake?
s plus 4 on the second row, that one, no, this,
I mean, this is
That
the
one,
wrong
that
one,
one.
right?
the left part, the second row on the left part. That one is also minus.
Okay, yeah, this came from the same thing. Yes, thank you.
Yeah, and then it comes s minus 1, which we saw in the thing. Yeah. Okay.
Okay, yeah. So we have -s, -4s, so it's -5s. Okay. And then we factor it. I guess I have to do this one a bit fast. So we get -5/2 plus minus square root 5/2 squared -6. So this is 25/4, and hooray, that's 1/4 under the root. So that's 1/2 in total, this part. So you have
Minus
-5
or -2.
So what you get is -5/2 plus -1/2 is 6/2 and 4/2. So it's
2 or 3.
yeah,
-2 or 3.
-2 or 3. Wait, minus, really? Am I right about this? No, it's a plus.
Okay, so it's-
Oh no, sign mistakes again. Yeah, so it's yeah, 2 and 3. And that means this is s -2 times s -3, which makes everything a lot easier. And
The
Yeah.
upper one is the, what do you call the thing over the division part, the upper part of it? It's also
It's
wrong because of the minus there.
You had the minus before, yeah.
okay,
That should be x minus 1, right?
Yeah.
but just s -1.
Plus 1 over s minus 1.
Yeah, but the s minus 1 division is already in the division right now.
Oh, okay, yeah.
So that's
Yeah,
x. No, that should be then squared.
no,
No,
then
the
it's
right part is 1 over s
plus-
minus 1.
What math is?
what?
Yeah, the right hand side is 1 over s minus 1 plus s minus 1.
So I mean, this is s -1.
Yep, exactly.
And we take this divided by the, okay, what we can do is we extend here by s -1. So we have 1 plus s minus 1 squared over s minus 1. So that's what we need to do here. And yeah.
ABC again.
And then we do the ABC stuff.
You do nice, yeah.
Yeah. Okay. So what can we do? We can do the following. We have A over first factor, which is s minus 1, plus B over s minus 2, plus C over s minus 3. Okay, good. And what should it be? Well, it should always be, I forgot, my brain power is used up at the end of the block. Yeah, it should be that thing here. Yeah, that's what we want to do. So it's 1 plus s minus 1, which we should calculate. And below we have this. And it's a plus. So we have to calculate the upper one, I guess. Yeah, I could just write that here. So we don't need this stuff because it was wrong. So that's s squared minus, that's thing, so plus 1 is 2. Okay, so that's what we have here. And then we get an equation like this, which is also quite long, but in this case, nicely solvable. And I guess this is where we officially stop. I might just finish it and let the recording continue for everyone watching this. So, yeah. Okay. So that stuff should equal that thing. So we again collect coefficients for s squared and have a plus b plus c equals 1 as one equation, and minus 2s minus 3s minus 5s, so minus 5 times a, and here we have minus 1s minus 3s minus 4b, and here again minus 3c should equal minus 2, and last one, 5a plus 3b plus 2c has to equal 2. Okay, and now you have to do linear algebra to solve it. I'll decide to add these two equations. That should be good. Yeah. So it's just adding numbers. That should be good. So let's give those equation names again. So this is 1, 2, and 3. So I'll do 2 plus 3. And that's, so the a's cancel, and I get minus b minus c equals 0. Okay, so minus b is equal to c. Good to know. And what's a good way to use it? Yeah, add 5 times 1 to 2. So I get plus 5 here, plus 5 here, plus 5 here. So I have b plus 2c equals 3. Yeah. And now I can maybe substitute with this one or just add this equation. So plus this equation gives me c equals 3, right? Cool, okay. And now I can backwards solve everything else. So with this equation, if I plug in 3, I get 6 here. So that's something I already know. I mean, I can use this one. So with this one, I know b is minus 3, and then I can use 1 to solve for a and get b is minus 3, 3, okay, a is just 1. Good, okay, that sounds reasonable. So you can plug in this stuff. Yeah, maybe let's do this over here. Yeah, so plug into our original equation, this one. So we have f of s, that's what this whole thing was about, getting some nicer representation of f of s. And now it's 1 over s minus 1 minus 3 over s minus 2, and c as 3, so that's plus 3 over s minus 3. Good. Okay. And now we still want to have lowercase f. And this is the Laplace transform of lowercase f. So now what this is about is now find f such that L of f equals that thing. Okay, and how can we do it? Now we have to use the reminder from the exercise text, which tells us that Laplace transform of e to the alpha t is something which looks like this. So it's actually 1 over s minus alpha. But no worries, the 3 is not important because Laplace transform is linear, so we can just look at only the summands in a linear combination. So what we can use is, for example, L of the function that maps e to 1 times t is, so, or applied at s, is 1 over s minus 1. So we know how to get this first part. right? It's a bit messy here. Okay. And we also know if you plug in something else here, like 2, you get 1 over s minus 2, which is this part, or 1 over s minus 3 if you use the 3 here. So what we then know is L of, so and now I make a guess for the whole thing. I hope that's not too surprising here. So I'll take the function maps. So the function which maps t to e to 1 times t for our first factor, and then minus 3 times e to the 2 times t for the second factor, and this minus 3, we can just put it in front, and 3 times e to the 3 times t. So if I Laplace transform this, plug in a value, it will be exactly this. I mean, I can write it out, that's probably better. So yeah, I'm not sure how to write these functions, but let's just do it like this. So I can use linearity to rewrite it as, yeah, so let's continue here. 3 times lambda t to e to the 2 times t s plus 3 times lambda t to the e to 3 times t of s. And that's exactly this thing then. And so we know this works as an f. Okay, and I mean, what you have to do now to finish off the exercise would be to test if it is really a solution. But yeah, let's skip that part.
Yeah.
Bye-bye.
Last question about
Yeah, sure.
They use the substitution of they tried s equals 1, s equals 2, and s equals 3 when they had the equation a over s minus 1 plus b to find the solutions to ABC. How does that trick work, or why do we guess 1, 2, 3, and how does it simplify our solution finding?
They guess 1, 2, 3. So at which point, like when I have this form?
I think the second form, the line below that part, and then they tried for s equals 1 and 2 and 3, and they found ABC really quick. Why does it work?
Okay, good question.
Oh, they are the root also. If you try S1, 2, and 3, they're the root.
Yes, there are the roots of these things. And are there also roots of this? Oh. So I don't see an obvious reason. I mean,
I see.
Yeah.
If you try 1, for example, s equals 1, then 2 of those terms get to 0, and then you have 1 term equals to something that does what constants to do. So here, for example.
Okay, I see. Yeah. You plug in something for s, and then you get a value. Interesting. Okay. Okay. That's a bit weird. So I wouldn't dare to do this in general.
Yeah.
But I guess it works because we divide by these things when we derive the equations. But I guess there's a reason that makes it work. Yeah.
Mm.
Okay, but yes.
In general, you just solve this for ABC and then you get that.
Yeah.
Okay.
I mean, if it's suggested in the solution, I guess that's something you can use. Yeah.
Mm.
Yeah, okay, that's shorter. I mean, that shortens
Yes, it's
equation
just
solving
math.
in the end, but yeah. But less general. But yeah, I guess it just works for some. Yeah.
Mm.
Yeah. Makes sense now to me that it should work, and I mean, algebraically, it of course works. Yeah.
Yeah.
Again, yeah. Just get a couple of numbers and have some left over A, B, or C. Yeah, okay. Yeah, it makes you a bit faster.
Yeah. Yeah, okay, so yeah, this kind of questions is now more clear. I think it was a bit
Yeah.
hard at first.
Happy to hear that. Yeah. Yeah, I guess I put some comments on YouTube and I stopped.